Hello. We're going to talk today about current and resistance as well as power. Okay, we're going to understand the relationships that are defined by Ohm's law and Joule's law. So let's dive right in. Current is a directed flow of charge through a cross-section. Here we see a picture of a disk, and this could be a wire, okay? Any material. Current is simply counting how many charges will travel through that cross section. So imagine it being a slice of a piece of material per unit time, right? The units that we use to measure current is coulombs per second or amps. 1 amp is defined as 1 coulomb per second. Okay, here it is in calculus terms. We see that we're taking the limit of the average current as the time frames go to 0, right? We're looking at smaller and smaller intervals of time, and that would become our current value. Okay, when we look at average current, we're acknowledging the fact that current in any normal piece of material is going to be made of many random motions going in many different directions. So we take the average current or the net current, right? And we take that over smaller and smaller time intervals to see the instantaneous current at any moment. Here's another visual of it. You should know that positive charge moving to the right will give you a current value equivalent to counting the negative charges moving to the left. They are equivalent. So it follows that a positive charge flow means there is a negative charge flow as well. Now, it's very important to understand that current is in response to potential energy changes. So I have a battery that's creating an electric field, and that situation results in potential energy. As I release these electrons, you're not restraining them anymore, you're giving them a path to travel, that potential energy gets converted. And as they travel, as the current flows, the electrons or charges, right, positive or negative, lose energy. It's very important to understand that current results in the loss of energy. And we are going to be tracking, going forward, the journey of the positive charges through a circuit. We're going to pass quickly over this exercise. The main point here, though, is that when you're counting charges for your current, the negatives going in the opposite direction of the positives count as twice the amount of charge. So a positive going to the right is the same as a negative going to the left, so that would be double the amount of charge. In letter A, right, we have 1, 2 charges to the left plus the 3 charges moving to the right. They all add together. In the second example, you have 3 charges moving to the left. That's a smaller current than letter A. All right, so now we're going to talk about current and voltage and enter into the world of Ohm's law, right? Here we see a simple circuit with a light bulb, and we have a battery, and you will recognize the setup from your lab. You're measuring current through the ammeter in series with the light bulb, and then you put the voltmeter across the light bulb to measure its change in potential. Now, the voltmeter goes across as if you're measuring the temperature from the right and comparing it to the temperature on the left. And you're going to always measure voltage across the element that you're interested in. The ammeter, however, is going to register the flow of current through it. And it has to be put in series as if you're putting it inside the stream, right, of flowing charges. It has to be very small in order not to disturb that flow. So an ammeter is like a wire. It's like a very small resistance, very close to the wire's resistance. And it's going to not affect the stream as it measures it. Okay? We use multimeters to measure these quantities. As you can see here, here's an example of one. We've done this in our lab. All right. Now, the most important thing to know about our circuits is that you have to have a closed path from the positive end of the battery to the negative end of the battery. You have to give it a path to return to the lowest potential, right? The downhill flow, the lowest potential point on the circuit. And in these, it's interesting to look at these circuits because you have a lot of wires and you have to think about which one allows the current to flow from positive all the way to negative uninterrupted. Let's take a look at it for a minute. In circuit A, we start from the positive, we go through a light bulb, but then we end again at the positive. Does this circuit experience any change in voltage from the first connection to the back connection? If you're looking carefully, no, it's going to see the same potential energy at the start and the stop of the loop. So there will be no current flow. In B, we see the wire connected to the positive terminal. It goes through the light bulb, and then there's a wire that comes out of the light bulb. See this wire here towards the back, and it goes towards the negative terminal. Now this allows the current to flow, but it doesn't actually need to go through the light bulb if these two leads here, I'm going to draw, make sure you're looking at the same thing. If these two leads are connected to each other, like with a wire, there is no path that has to go through the light bulb. It simply continues its path, and this will basically burn out the battery. Could cause a very dangerous situation, in fact. Now, looking at this circuit, we have the positive going through the light bulb. Now, there is no connection between these two leads except through the light bulb. We will see light in this situation because it's going to force the electrons to use their energy in the light bulb. And then it goes to the lowest potential point. And finally, let's check this one out. We've got the current flowing from this positive terminal. It does go through the light bulb now. I see that. And then it comes into a multimeter, right? And if this is set to amps, this is just like a small resistor. No problem. And then we're going to come out of the multimeter to the back of the battery. This will also light the bulb. Any questions on this one? So that brings us to Ohm's law. And we're going to understand this mathematically, but before that, I want to make the very important point that the current that we are tracking now in these formulas is the positive charge movement. Now that's theoretical. That's an abstraction that we make in these in this part of physics, and it's not really based on the physical reality. Positive charges are the heavier charges. It's the electrons really that flow, leaving behind a positive charge. So you can imagine as the electrons move to the left, it's leaving behind a positive charge to the right. And it looks like the positive charges are moving if you make the electrons, if you imagine the electrons were fixed in space, right? That's what it will look like. If you were riding the electron, think about me riding the negative electron. It's moving, but I don't know that it's moving because I'm sitting on it. It's the positive charges that I see moving away from me to the right. Okay, so that's the convention that we use. So thinking about positive charges only, we're going to make this very important statement. Current of the positive charges flows from the higher potential to the lower potential. Always. The higher potential in the previous example was the positive node of the battery. The lowest potential point is the negative node. So now looking at this, we see a little segment of a conductor that's got current flowing. VB and VA are the two potential voltage values on the left and the right. Because I see the current flowing from left to right, that means that VB is higher than VA. Okay? And your multimeter that you use in the lab will assume that as well. The red lead of the multimeter is supposed to be placed on where you think the current is entering, or the higher voltage value. And the black lead goes on the opposite side where the current exits. If you have that wrong and the current actually flows the other way, your voltmeter will read a negative voltage because it's going to do VB minus VA. So think of it as hot minus cold. It's going to try to subtract the cold side from the hot side and get the temperature difference. That's an analogy, right? It's getting the voltage difference. But if you really had it reverse and the current is really going the other way, it's going to give you a negative answer because it's just doing a simple subtraction. Fine. So now we're looking at Ohm's law. Right here, the change in voltage, that's VB minus VA, is going to be equal to the current flowing through that piece of conductor multiplied by the resistance. The resistance is a property of this material that determines how the current responds to the voltage difference. Now, I really would prefer to learn Ohm's law using the second equation because this is what's motivated Ohm's law. When they did the experiments, when Mr. Ohm did his experiments, he measured how much voltage change the material needed to send a certain current through. I like to say, it's the work I do to get the current through. A good rhyme always makes learning easier. It's the work I do to get the current through. And every piece of material is going to require a different amount of work. It takes less work to get current through a copper wire, than it does to get it through cotton or air or paper or carbon. So the ratio of the amount of work it takes to get an amp through is called my resistance. We use the ohm unit, which looks like a horseshoe. This is my horseshoe right there. And it basically is named after the scientists who discovered this relationship. But it means 20 ohm resistor means that it takes 20 volts to get 1 amp through that piece of material. That's 20 joules for every coulomb of charge to get 1 coulomb to flow every second. And that would mean in this example, if I have a 6 amp current, I'd need 120 volts. Right? Now, Ohm's law, looking at this equation, it tells me that I have a linear relationship between the voltage and the current. So if this is voltage and this is the current, this line here is going to have a slope equal to the resistance value. Okay? For every increase in current, which is measured in amps, I'm going to have an increase of R units in voltage. All right. These are examples of electronic parts. These down here are resistors. These are the ones that we use in our lab. Okay, these are examples of many different types of resistors. The ones below here with the cylindrical body are the ones that you're going to be mostly using in electronic labs. Okay, but resistors come in all shapes and sizes. And let me not neglect to show you the symbol for a resistor that you'd use on a schematic in a simple engineering diagram. That's my resistor there. And this slide illustrates the point I made before. Now notice I've changed the axes. I had voltage on the y-axis before. Now it's current. So if current is the y-axis, then the formula becomes I equals V over R. The slope now becomes 1 over R. Okay? Now it's very important to note that I write V because as an electrical engineer, this is the way we tend to write it, but it's always representing the change in V across 2 points. Always. Ohm's law says that the change in voltage across a segment, across a piece of material, is equal to the current flowing through it times this resistance value. All right. Now, the left side shows me an ohmic device. The right side, what do we see? We see something that has a changing slope. And so this is not going to give me a perfectly ohmic relationship where R or 1 over R is constant, right? So we do have materials that are not ohmic, do not obey Ohm's law. Okay. So here's a diode diagram. Okay. Diode is an element. You have light-emitting diodes, which we're very familiar with, but they don't have to emit light. But it's an element that takes a certain amount of energy to allow current to start to flow. And once it starts flowing, it doesn't require any more energy. Okay? So the resistance drops, if you would, and it drops basically almost to 0 as you push through the threshold voltage, right? As you give it that threshold voltage, now suddenly the resistance drops, so it becomes like a conductor. All right. So in the figure below, does the resistance of the diode increase or decrease as the positive voltage increases? Well, remember that this slope here gives me 1 over R. Okay? So as I become steeper, okay, my slope is actually going to infinity, right? My slope is becoming very large. So if 1 over R is my slope and that's becoming larger, what does that tell you about R? It has to be getting smaller. Okay, so remember the principle. The smaller the denominator, the larger your quotient. So let's hear, this is an example of a very small denominator, 1 over 0.01, that's equal to 100. As opposed to, as opposed to 1/2, 2 is much larger than 0.01, which is equal to 0.5. Okay? Keep that in mind. It'll help you in many math problems. Let me make my notation neater. All right. So there we have it. So we're going to go past this so that we can get to very important problems related to your testing that is coming up soon. So what we have here is resistivity, and we've done this in our third lab. We've talked about resistivity. Understand simply that resistivity is like internal friction, right? It is how much work a electron, a charge, positive or negative, right, has to do as it goes through a medium. This depends on the medium's electronic structure, and it also depends on temperature. We will see that even for an ohmic device, things can change when you get very warm or when you get cold. So the resistivity is an intrinsic property to the material. The resistance, though, of a segment of a circuit has to do with that resistivity and the geometry. Because as I said, you can have a certain amount of atoms that are pushing back on the charges, but if you have many different lanes, pathways for those charges to travel, it can reduce the resistance, right, of that segment. And likewise, if you have a certain resistivity of an atom, the series concatenation, right, putting many of those atoms together in a line will also increase the amount of resistance, friction overall. So resistance is a concept that includes the chemistry of the atom, right, of the element, and the geometry of the piece of material. And it is proportional to the length. That means it increases with length. And it is inversely proportional to the cross-sectional area. That's the number of lanes in the highway. All right, so we're going to go past this exercise and get to some important calculations. Okay, we're also going to skim this quickly. Here is an example of a resistivity equation that shows the dependence on temperature. So resistivity does change with temperature. The T minus T naught is showing you the dependence there. But we're going to continue past this and look at circuit diagrams and understand how we can simplify circuits that have multiple resistors in it. And we're also going to look at the concept of power. So in this diagram, we actually can think very quickly about energy and power. We have the battery between nodes A and B. We see a current flowing, which is labeled I. Okay, I is used for current, even though it's not in the word current, but we are going to reserve the letter C for many other things. So we use I, and normally we talk about, we think of it as the intensity of the current flow. So I is the current, and it's measured in amps. And then we're going to have this resistor value, R. How can I determine how much energy is being consumed by this circuit? Well, here's the first thing we need to understand. Voltage, or the change in voltage, right? I'm not going to write this delta V all the time. I'm just going to keep reminding you that as I write V here, it refers to the change in voltage between 2 points. So the change in voltage is always referring to the amount of energy that is being spent or inserted into the system per charge pack. That's a coulomb right there. Now, the current we just learned is how many charge packs flow every second. So if I wanted to know how much energy is being spent, how much heat or light, everything that we experience in terms of energy, how much of that is coming out of this resistor, I'm going to want to know, this is going to tell me the joules that are being spent or invested by the battery every second. This is a measure of power, which we measure in watts. Okay, so let's quickly put through our units here. Coulombs per second is amps. Volts, joules per coulomb is simply volts. Thank goodness, no new words to memorize there. Okay, volts. So now we have joules per second equal watts, which is power, and it's a measure of the energy that's being either spent at the resistor, coming out as heat or light, or being invested by the battery, right? How do I get that from the information of volts and current? If you look at the units, you can see that it has to be a multiplication of the two. And the analogy I like to use is, if I have strong workers, and each worker is coming with his own, strength, and that's going to be measured in volts. So it's joules per worker, right? That's his strength or her strength. And I'm going to need to get a certain amount of work done every second. The only question I have, I know how strong each worker is. The question I have is, how many do I have? How many workers do I have? So I'm going to have to have a current value, which measures the quantity of those worker B charges, right? Each charge is like a strong worker that's about to do some heavy lifting. All right, so voltage times current equals power. And it's a rate of energy flow because it's joules per second. Okay? So here is the information we just went over. We have power equals current times the change in voltage. Now, there's a very important unit that we use to measure the energy, total energy that we get out of it, and that's kilowatt hours. We're going to look at that, and that's what they use at the power company to charge you. So before we do that, let's take a look at this formula and see how we can rearrange things to give it many different forms. So we know that the current and the voltage have a relationship through Ohm's law. And some of us like to use these triangles to remember these short formulas. Ohm's law can be thought of as V equals IR, and the pyramid here shows the V as the product and the I and the R as the factors. And if you wanted to find any of these, you can just take the diagonals as division problems. So V over R equals I, V over I equals R, and I times R equals V. All right, so that's a little hack some students like to use. And we're going to use these relationships to convert the I times V relationship using the fact that V is also I times R. I can now rewrite the power as I times R. I will substitute this Ohm's law equation for this change in V. This is still true. So that gives us an alternative formula for power. P equals I squared R. Likewise, we can take the current in this formula and rewrite it using Ohm's law as V over R. Okay, remember you can do the division here and get the other item. So that would mean that V is being multiplied by itself twice. You get V squared divided by R. So these are equivalent statements of power. This formula is known as Joule's law. This power formula, Joule's law. Now let's talk about this kilowatt hour really quickly. I told you that watts is a rate of energy flow. It's how many joules of work I can do per second, right? The voltage tells me how strong my charges are, how much energy they have, each one of them. And the current tells me how many are flowing per second. So together I get the amount of energy flowing per second. It translates into heat, right, or light. But the total energy that I use or that I spend is going to be based on how long that power is flowing. So you must multiply by time. Watts is joules per second, so you'd multiply by seconds to get the number of joules. And as you can see, there's a convenient grouping that we use in our society of 1 hour, and kilowatts is another convenient grouping that we like to use in terms of this measure. The electric company is going to charge you for every kilowatt hour of energy you use. That's 3.6 million joules. Every kilowatt hour is 3.6 million joules. But they just count up kilowatt hours in your household. If I use 1,000 watts, that's 1 kilowatt for 1 hour, they consider that to be 1 kilowatt hour, and they charge you at a certain rate. You can look it up. I think we looked it up the other day for PSE&G. It was something like 17 cents on the internet. I don't know if that's accurate, but it's a number on the order of, less than 20 cents per kilowatt hour. But that can add up over time. Okay. All right. So now we're going to look at simplification of circuits, resistor circuits, right? And we're going to think in the same way we thought when we looked at this with capacitors. We've already done quite a bit of circuit simplification in chapter 16 with capacitors. We're going to do it again with resistors and think in the same way. We have two possible configurations, parallel and series. Actually, we have three possible configurations, parallel, series, and neither. There are situations where your circuit elements are not in series and they're not in parallel. But we'll study the first two first. So in this situation, we have the voltage source connected to nodes C and E. And what you're going to do is track the entry points of the current and the exit points of the current going through the elements. If they are tied together with nothing in between, nothing in between means I don't have, I don't have any other elements breaking the current here, right? The ends F and D are connected through a perfect conductor. In that case, if these two wires are connecting the inputs and the outputs, these are considered parallel. And you can have more than two parallel elements. Now, when I see two parallel elements, the first thing I think of is more current paths. I actually can get more current out from that battery, which means the total resistance, if you look at this as one box, right? And I don't know anything inside the box, but I just think of this as one box connected to my battery. The total resistance is smaller with these two parallel branches. That's wonderful. So if I want to increase the current flowing through a circuit, I simply add more and more parallel branches. Now, the total resistance for these two branches is going to be given by this formula, which you should recognize. I told you it was going to be an important formula. Well, here it is again. The total resistance is going to be the sum of the reciprocals flipped. So it's the reciprocal of the sum of the reciprocals. This minus 1 power means to take the reciprocal of that argument inside the bracket. So here it is written out. Okay, here it is written out. So this goes for any number of resistors. 1, 2, 3, any number of parallel branches. So if I had 3 branches, this would be 1 over R1 plus 1 over R2 plus 1 over R3. And then you take the reciprocal of that. So to show that, we simply do a notation like this. Say plus 1 over R to the n, where n counts the number, it's the index, right, of the resistor. And you put a dot, dot, dot to show that there would be other fractions in that sum. And you would take the final reciprocal after you summed all of them. Okay, so I'm going to put a plus here to show this information. Right? Now, if you only have 2 resistors, there is a simple shortcut to this. We did this already with the capacitors. We'll do it again. When you do the common denominator, you end up with R1 times R2 over the sum. Now, if you remember for the capacitors, this formula was applied when the capacitors were in series. So this is an important difference. Resistors in parallel will act like capacitors in series as far as their formula goes. Okay, they're not the same element, so I don't want to imply that they act physically the same way. They act very differently, but the math that you would use is the same. Okay, so we have this formula for simplifying this circuit, and let's just answer this question really quickly now. For the 2 resistors shown in the figure, rank the currents at points A through F. So the current IA is the current flowing out of the battery and going through the 2 branches. It's the total current. That is the total current that it's being diffused out, right, into the 30 and 60. So that actually has to be the largest current. Now, IA is going to be split between 60 and 30. Which resistor is going to allow the largest flow of current through it? Isn't it going to be the smallest resistor? Right? It's going to give the least amount of resistance, friction. So the current E is going to be the larger of the 2 currents, E and C, right? Between those 2, E is the larger. It's actually twice as large. Oh, and now that I'm looking carefully, be very careful. Always pay attention to your units, because I made a mistake and you could have made it too. This is not ohms. This is watts. Look at that. And now I'm going to change my answer, because watts is current times voltage. So if I'm getting 30 watts out of this resistor A, and my voltage that's seen across it is going to be the same. Notice that the battery is giving the same energy difference to both ends of these resistors. That means the only difference can be in the current, and therefore the current at E is half the current at C. Now I'm going to flip the script on you a little bit, going back to what I started talking about. If we know the current at E is less, what does that tell you about the resistance? The resistance has to be greater at A. In fact, we can see the resistance has to be twice the value of the resistor at B. Okay. Actually, let's do that math really quickly. That's an important problem to solve. So we know that the power, we're going to use this formula, I squared R. Okay? And if we know that 30 here is the wattage here, let me see if I'm right. If the resistor is really going to be twice the resistance. 30 watts equals I squared R. Oops, messy. All right, now take a look at this. We're going to take a look at the 60 watts. And we know this is, and then I'm going to make this R1. 60 watts is another I. This is a different I now, right? Because they're different paths. So I don't have to have the same current in different paths. So I'm going to label this I1 and I2. And this is R2, which I don't know. I'm going to figure that out. And we got 60 watts. So one thing that's clear about this is I have two variables, two equations. So I'm not sure if I'm going to be able to solve this very easily right now. What if I could reduce this to one variable? Well, thinking about it, I actually can, because the other equation that I have is IV. Okay, look at this. IV equals power. And now I know V is constant for both of these paths. It's a really great problem. So let's actually use that one and reduce the number of variables in this story. So we're going to do P1 equals I times the constant V. And P2, so this is V constant, but I don't have a constant I, so I'm going to say I1. And P2 is I2 times V. Now I can see clearly, because the V's are the same, if P1 and P2 have a ratio of 1 to 2, then the currents have a ratio of 1 to 2. All right, so knowing that, we can talk about the resistors now. So 30 watts, we're going to let that be I1. And for the 60 watt, what I'm going to do is let that be I1 divided by 2. I'm sorry, I1 times 2, it's double the current, right? Almost got me there. Now, watch what happens. We're going to square this. Let's square this. Do you all agree that we just proved to ourselves that the currents follow the power in this scenario? All right, so if I1 and I2 have the 1 to 2 ratio, okay, what does that tell me about R1 and R2? I'm going to give you a second to see if you can work that out and put it in the chat box. So we solved the problem here, and let's talk about it. Okay, we're almost done solving it. We have one step left. So we understand that the currents have to have the 2-to-1 ratio because we see Joule's law is pretty simple here with the I and the V. And we're going to now rewrite the power equation using the resistance R1 and R2, which is actually the A resistor and the B resistor. Okay. And I'm going to use the fact that the currents are have a 2-to-1 ratio. So I'm going to remove that variable. So now I have for the smaller power value, I have just I1 squared. And then the 60-watt branch is going to be 2I1 quantity squared. Now, here it is written over here. Be very careful that you put the 2 inside the square. The current I2 is 2 times I1. So the square of it is 4 times I1. Okay, now we use our algebra here, right? We can see if I divide by 4, the 60 equals 4I1 squared R2. If I divide by 4, I end up with 15 watts equals I1 squared R2. Now look at this. I see two equations. I1 squared is the same in both. The only difference is R2 and R1. And I have a 2-to-1 ratio, which means that the resistors have a 2-to-1 ratio. The resistors have a 2-to-1 ratio, but it's not the way you would think. Well, it depends on how good your intuition is on this, but the larger power value has the smaller resistor. The larger power value, the 60 watt, has the smaller resistor. It is half the size of R1. All right. So having said that, we're going to do one more example with real numbers now. I'm going to practice finding the power through two known resistors. Okay, so let's do that. So here's our example problem. We're going to find the current through each of these two branches and the power that's going to be spent through the branches and the total power produced by the battery. Now remember, power is energy flow per second. So it's not the total energy I'm using. I'd have to know the time frame in order to get that. But let's talk power. So the first thing to do to get current when you know resistance is apply Ohm's law. Okay. You have the initial form this way, but because we're looking for current, I'm going to use this relationship, right? It's just algebra. The voltage across the resistor divided by the resistance value. So this is easy math. 12 volts is across this resistor, and I'm going to have a 6 ohm resistance. So that's a total current of 2 amps. Okay, flowing this way from higher voltage to lower voltage. Now, for the 2 ohm resistor, you see it's going to be much larger. It's going to be 6 amps. Okay, so now we're ready to do the power through each branch with simple multiplication. You can use any form of the Joule's law formula. We have resistance and current, but we also know the voltage. So I will do the simplest form of voltage times current. So in this first branch, I've got 24 watts. And in the second branch, six times 12, 72 watts. Okay. And now we can look at some of the relationships we looked at before. Let's do the ratios and see if things match up the way we had them before. Right? I'll let you do that for a second. Look at the currents, 2 amps, 6 amps. I have a 3-to-1 ratio, don't I? Right? With the currents. And in my resistors, I have the same 3-to-1 ratio, although it's reversed. It's a 1-to-3 ratio, right? It's inverted for the resistors and a 3-to-1 ratio on the currents. Likewise, the powers show the same 3-to-1 ratio, and it follows with the current. All right, that's a very straightforward application. Now, if I had multiple branches, the math is exactly the same for each branch. Now, the question I ask to you is, what is the total power produced by the battery? There are a few ways to do this, but right now I want you to think of Ohm's law, and I want you to think of a special relationship that we have in any circuit between the currents. If you are splitting current through many branches, the total current that's going into those branches has to equal the sum of all the branches. This is known as Kirchhoff's current law. It just says what comes in has to come out. So I have a total current of 8 amps. 8 amps coming out of this battery. And so to get the total power, you'd multiply 8 times 12 volts, the battery's voltage. We have 96 watts. Now, do you see how this is simply the sum 24 and 72? There are many simple ways to get these answers. We're going to do one more thing. What's the total resistance of this circuit, these parallel branches? Well, I'm going to use the simplified form of the formula. It's the product over the sum. So we see we have 8 over 18. Excuse me, it's not 8, it's 12 over 18. Right? And we can simplify that. Divide out a 6, top and bottom, right? Could have done that over here as well. So we see that's going to be 2/3. 2/3 of an ohm. It's important to note that whenever you have parallel branches, the total resistance always drops. It's always lower than the smallest resistor in the set of branches. I want you to make that make sense to you. If I have this 2 ohm resistor, that's the smaller resistor, right? If it's all by itself, the resistance of the circuit is 2 ohms. If I add a 6 ohm resistor, is it possible that the resistor, the total resistance can be higher than 2 ohms? I'm not going to do worse by opening up another lane. I have to do better overall. So the total resistance for the whole circuit is going to be less than the 2 ohms. That's always true. That formula, the parallel formula for resistors or the series formula for capacitors always has that property that the final answer is always less than the smallest value in the system that you use the formula for. It's kind of cool when you think about it, and it's a good way of checking your work. All right, so now that I have the total resistance, I'm going to use Ohm's law to figure out this power again. And it actually just validates all of our formulas. So we're going to see this circuit as the equivalent of a 12-volt battery across a 2/3 ohm resistor, or 0.67 ohms. Okay, you can use the fraction or the decimal here. Okay, The decimal will be less precise than the fraction, but I'm not going to be as fussy about the precision here. So now we're going to look at, in fact, I am going to use, because the numbers are so nice, the multiples of 3 and 2 here, I'm going to use a fraction. So we're going to now think about this again in terms of Ohm's law and Joule's law. What is the current flowing through this second equivalent circuit? It's going to be 12 divided by 2/3. So it's 12 times 3/2. Okay, so I'm making sure my values are right. And see, and go. So we just caught our little error here. And the reason why we knew there was an error is because we were about to get a current value that's different than what we worked out in the top scenario. This 12 times 3/2 is going to give me 18 amps, which is absolutely wrong because then it would not be equivalent to the first circuit. Okay, when you say a circuit is equivalent, that means the voltages that you're getting and the total current coming out of that source are going to be the same. So now, the error happened here when we calculated the total resistance. Must have been a typo of some sort or a brain freeze, but this formula requires that you use the same values for the resistor R1 and R2 in the top and bottom. It's R1 times R2 divided by R1 plus R2. Okay, so that was just a brain freeze. So now we're going to do this correctly, and it is 12/8. Now I want you to notice something really quickly. Okay. Notice that if I went to the original circuit where I saw the total voltage and the total current, those numbers are 12/8. That's the definition of resistance. It's the current you get for the amount of voltage that you're pushing, that you're producing, right? So that's a confirmation for us. This is the right value. So this is not 2/3. It's actually, dividing out the 4, 3/2. Now everything looks perfect. We're going to put the 3/2. It's 1.5, right? 1.5 ohms. It's still less than the 2 ohms. Make sure you check that. It's still less than the 3 ohms. And so this 2/3 becomes 3/2. All right. And now we're going to take the formula for Ohm's law again. And now it's V over R. We're going to solve for our current. So it's V over 3/2. Okay. And that just is 2/3 times 12. And I get 8 amps. Okay. So let's look at our units and make sure we are clear on our units, right? We got this volts, we've got ohms here, and we end up with amps. And now all of the math is the same for Joule's law. If I multiply 8 times 12, I get the 96 watts. So there you have it. Power in a parallel system. Now, very quickly, we're going to look at power in a series system. And then finally, we're going to put them together, parallel and series system. Okay, so we're going to look at the same car battery. And I'm going to use this circuit below here. And I'm going to put 2 resistors back to back. That's what a series circuit looks like. It's the simplest configuration. It's just back to back. Well, I don't know. I guess some people think parallel is simple. But when you just have one loop, one path, we now have one current that flows through all of the elements. And we're going to use the same 6 ohms and 2 ohm resistors. Now I need to answer the same questions, but this time we don't have branches, we just have elements. So the question is, what is the current through each element? What is the current through each element? And what is the power being dissipated through each element? That's heat and light, right? And what is the total power produced by the battery? So I am going to let you pause the video to work these things out as best as you can. I'll come back with all the answers. All right, so now that we've cleaned up our board, we can work through this problem. Very simply, the rule for series resistors is the simplest rule you can have. And it should be intuitive to you because you know that resistance is going to be proportional to the length of the material that you're going through. You should see this series circuit as an extension of a resistor. Basically, it's like 2 resistors placed back to back, which increases the total length, right? If it's the same type of resistor, you're just adding the values. Now, you can tell me, well, what if it's not the same type of material? In that case, we're going to use another property of circuits to understand how to simplify this. The fact that I have 12 volts in my battery means that I'm only going to be able to get 12 volts out of all of the elements. It's a conservation of energy. And we have another special name for it in circuit theory, and that's Kirchhoff's voltage law. I'll write that out for you. We've said that name several times. Kirchhoff's. It's confusing because there are 2 H's in it. Voltage law. And previously we had talked about Kirchhoff's current law. Both of these just talk about conservation. What comes in comes out. If I'm putting in a certain amount of current, that's like a flow rate, right? Then I need to have that flow coming out in all the branches that I'm connected to. In voltage, if I'm putting in a certain amount of energy from the battery, all that energy is going to be seen in the elements of the loop where the current is flowing. Not going to have less, I'm not going to have more. So if we think about Kirchhoff's voltage law, we're going to be able to write across each element the total energy lost using Ohm's law, which we know is true. So I have the voltage change across a 6 ohm resistor has to equal the current through that resistor times the 6 ohms. So that's V equals IR. Okay? So the voltage change, which I don't know what it is right now, but let's just say V equals some current times 6 ohms. And I don't know what the current is either, but I'm going to figure things out in a second. Now I'm going to use the same law. I'm going to use the same law down here near the 2 ohm resistor, but it's going to be the current times 2 ohms. That's going to be a new voltage, and I'm going to call this V2 because it's a different change. It's a different amount of energy, right? Because it's based on this small resistor, right? So I'm going to say V2 equals I times 2 ohms. And over here, this is going to be V1 equals I times 6 ohms. All right. Now we're going to use this Kirchhoff voltage law, and we're going to write that 12 volts has to equal V1 plus V2. And then I can say 12 volts equals I times 6 ohms plus I times 2 ohms. I'm going to put parentheses. Actually, I'll use the X for multiplication here because we're not using X anywhere else. Now, if you agree with me, what we can see is I is going to be equal for this whole circuit, right? It's one loop. Can't have different currents. We talked about that earlier on. We have to have the same current through a loop. Now I'm going to imagine another circuit with an equivalent resistor. If I have another circuit with one equivalent resistor, well, I'm just going to make it one resistor like this, and the same current, right? If I have this situation, now these two circuits are the same. They look the same as far as power goes, and the current values that I'm having. So what would be this equivalent resistor? I'm going to call it R equivalent, REQ. Well, if I simply multiply 12, let me restate that. If I multiply the current times REQ, that should give me the total voltage of 12 volts. Same law, the conservation of energy here. So looking at these two equations, okay, let me rewrite this one over here. 12 equals I times 6 plus I times 2. If I want these I's to be the same, that means that REQ had better be 6 plus 2. Okay, let me just do a little simple algebra here. We're going to just factor out the I. This algebra is simple. I times 6 plus 2. These are the ohms from the first circuit. So we see that in order for these I's to be equal, the REQ has to match this 6 plus 2. Very straightforward. We could understand it using the physics explanation of resistivity and length and all that. But if we didn't have the same material, we could still prove this has to be true. You just add the ohms of each series element. Now you have the two principles you need for simplifying any resistor circuit. So now that we know that, we're going to mix it up. Oh, did we answer our questions yet? Oh, before we mix it up, let's answer the questions. We've got to have the current through each element. Well, that's simply going to be equal to 12 divided by the total resistance, REQ, which is 8 ohms, which is now 3 over 2 amps. It's 1.5 amps. Okay? Notice that is a lot lower than the last scenario with the parallel branches. We had, how much current, wasn't it? 8 amps? Was quite a bit, wasn't it? Now the power through each element, you just take the current flowing through it times the voltage across it, right? And since we know the current and the resistor, why don't we use the form of the Joule's law that only uses current and resistance? So that would be 1.5 squared times the 6 ohms. Okay, and I'm going to let you work that out. Okay, while I write the formula for the next one, it's the same 1.5 squared times the 2 ohms. Okay, I'm going to give you a minute to get those values for me. Please put them in the chat box or shout it out. I always prefer to work with fractions. And what do we get? 13.5 watts. Okay, this is for the 6 ohms. Hope you agree with me. And for the 2 ohms, what do you think you're going to get? Yep. Okay, so let's see if we all agree with Marie's answer. It should be a third, right? But what I'm going to do is just divide the 2 into the 4 to get 2 to get 4.5. Perfect. So notice that these powers are much lower than in the parallel scenario. Now let me ask you what the total power is coming out of the battery. Total power coming out of the battery. Okay, so yeah, something is, if you're not seeing conservation of energy, then we have an error somewhere in our calculations. So let's make sure we got that right. So the total current we calculated to be 1.5 amps. 1.5 amps. So that's 1.5 times 12. Do you get 18 watts? That's 18 watts. And all we had to do is add the total power coming through the elements. You get the 2 halves make 1, and you got 17. That's 18 watts. Whether you're parallel or series, the amount of power coming out of the source is never more or less than the power going through the elements. Remember that. Makes life a little easier too. You can, once you have the pieces, you can just add them together. Great. So now we're going to mix it up a little bit, right? Let's just give you a chance to catch up with your notes here. Also, the other pattern to recognize is that for the parallel scenario, the bigger the resistor, the smaller the power, right? It's totally opposite with the series circuit. You see, I have more power coming out of the 6 ohms because they have the same current. So there's going to be more energy spent going through the 6 ohms. That means I'm spending more power there. Okay. All right. So now we're going to mix it up in this circuit, which has 2 parallel resistors, and it has this 5 ohm resistor that is going to end up being in series with a consolidated resistor, an equivalent resistor for the 10 and the 20. So let's just take it in pieces. We're going to simplify the 2 parallel resistors first, because they're the ones that we can obviously see are in parallel. Their 2 top ends are tied together, and the 2 bottom ends are tied together. There is no element between them, okay, where the current enters and exits are tied together. So we're going to use our parallel resistor formula, rather. And that means it's 10 times 20. This is the shortcut formula for 2 resistors. Okay, 10 times 20 over 10 plus 20. And we're not going to make the same mistake we made last time, right? We have to use the same numbers on the top and bottom. Your product over the sum. Now, when we get the value, what do you expect? Is it going to be more or less than 10 ohms? A lot of students like to think of it as the average, but that's wrong. It's not the average. If you were 10 ohms by yourself, if you were the 10 ohm resistor by yourself in the circuit, you can't do worse when you add a helping branch, right? The second branch is just going to give more paths for the current. So you're never going to get worse than 10 ohms. It's going to be less. So the value becomes, let's look at the numbers, 200 over 30. Okay. So what we see here is 20 over 3. 20 over 3, right? And what do we get? 20 divided by 3 is 6 2/3, right? 6 2/3. 6.67, we'll use that fraction. So there we have it. We have a number less than 10. Okay? That means that we could replace this part of the circuit with a resistor of 6.67 ohms. I will do that. Okay? So I will do that. Take that gone and imagine that this is the new resistor now. It's an equivalent resistance of 6.67 ohms. Okay, let's erase this. All right, and erase that. So you need to realize that an equivalent resistor means that if I were to look at the previous parallel system with the two branches, and I made it a black box, it would look just like I had one 6.67 ohm resistor in that whole box. The currents and the voltages will be the same. Fantastic. So now if we look at this, what do we have? We have a series circuit, don't we? Okay, let me make it a nice, neat circuit here. I'm going to type this in. And how do we deal with two series resistors? Well, we talked about it previously. Remember, we just talked about it up here. We simply add whatever resistors are in series. And how do we know they're in series? Well, there's only one current path. We can only go from the 5 ohms directly to the 6.67 ohms. There's no other branch that the current can split off into. And so the new resistance, the net resistance, is 11.67 ohms. And we can write a new circuit, can draw a new circuit with a 12-volt battery and one resistor equal to 11.67 ohms. Now, let's find the total power being dissipated by this battery, or being generated rather. How much power does this battery produce? I'm going to use the formula that says V squared over R, because that's the information I have. So it's 12 squared. Let me write the formula out and then we'll actually do the numbers. This is another form of Joule's law. Okay? Power is the voltage across the element divided by the resistance, voltage squared. So that's 144 over 11.67 ohms. Okay? And that's a calculator problem. Whatever number you get will be in watts. And it's something close to 12 watts. Okay? It's something a little bit more than 12 watts. All right. So there are very important points that I need to make. We've done all the problems that you will need to do for this exam. Well, we can show you some more configurations that you should be familiar with. Okay. Well, First, who has the exact answer to this question? Let's write it out. 12 point, what is the answer? 12.33. Very good. Awesome. Now, this configuration had two parallel resistors that ended up being in series with the 5 ohms. How could I have also drawn a circuit? I could have drawn it as two parallel resistors in series with another two parallel resistors. And in this case, we would solve the two parallel resistors first. Right? This is not a mountain range. It's supposed to be two resistors. Okay. Each parallel system would be simplified first using the formulas that we've worked with, and then you would have two series resistors after you replace the parallel systems, right? Whatever you end up getting here, this new value would become a series resistor with this new equivalent resistance here. Then you would add. Remember that any values, any question that asks you for power or voltage or current is simply asking you to use Joule's law or Ohm's law. Okay? And it's a very straightforward problem. Now, the mistakes that certain students make, if you were to start with this circuit here, 12-volt battery and the 5 and 6.7 ohm resistor, if you're asked for the power through any one of them, and you wanted to use this V squared over R formula, you have to be very careful not to think that 12 volts is going to be across each of those resistors. Remember that the energy drops as you go through the circuit. So there's a total loss of 12 volts across these two resistors, but each one takes a portion of energy. Now you can simply combine the two resistors and find the current using 12 volts over the entire resistance, which we know is 11.67. And once you know the current, then you can simply take that current value, which is the same for each resistor, and use Joule's law that way. I squared R is a good formula in that case. But if you don't remember I squared R, you can simply do V equals IR, which is now known to you. You'll know the new voltage across, the difference in the voltage across the 5 ohms. You'll know it because you'll have the current and you'll use the 5 ohms. Okay? And you'll see that the voltage is a little bit less than half of the 12. It's approximately 5, it's between 5 and 6 volts. The 6 ohm resistor, or 6.67 ohm resistor, is going to have a little bit more than half, right? You can see that the ratio of the resistors determines the ratio of the voltage across them. Okay? So that's an important error to avoid. Well, this is all we needed to review for our test material. I would like you to watch the video carefully, maybe a few times, and then ask any questions you need to via email or in the assignments that I might post regarding these videos. So with that, have a great evening and we'll see each other in class.